All right, so 4.2, basic differentiation and rates of constant change. This is one of my favorite lessons to teach because it's one of the first times that you actually get to see some very useful mathematics. Because a lot of times they're like, well, what's the point of doing this? And a lot of the upper level math that you've done so far, there's probably been a lot of times you're like, this is long, this seems pointless. Why do we have to learn this and what's the point? I'm going to answer a lot of those questions with this section because we're going to take a lot of the ideas we've been looking at with limits and derivatives and the tangent line problem and then actually apply those to real life situations. And it's one of those cases where it's going to be really easy to show this is why we learn the math because that's how the world works. We'll have some equations, things that deal with gravity and some other things like that, which we'll be able to use to model a lot of naturally occurring phenomenon. It'll use the calculus. And it's one of those places where those are the questions people had. So the calculus was created to answer those questions, and it led to answers to other questions, all kinds of other stuff. We'll still use the limit definition for a derivative a little bit, but it's only going to be used to prove that these shortcuts work. So this stuff will be a lot easier than what you did last time. But the reason why this stuff works is still because of last section. So we'll look at those proofs in your book as we go through this. The first rule is the constant rule. It's about as easy as you can get. The derivative of a constant function is always 0. Derivative of a constant function is always 0. Now we actually did prove this in your homework yesterday. I think you had what, like f of x was equal to 3 was one of the problems, and we got 0. And that's going to work for any constant because up top you got 3 minus 3. Anything minus itself is always 0. So the limit as delta x approaches 0 of 0 is always going to equal 0. And that works no matter what constant you have. So just whatever number you want to use, that's going to work. If I give you f of x equals 17, what's f prime of x have to equal? 0. That's it. Derivative of a constant is always 0. Always. Another way to think about that is, think about derivative as a rate of change. If we said derivative gives us the slope, what's the slope of any constant? 0. That's another way to kind of remember that. Derivative is a rate of change. If it's constant, the rate of change is 0.
So, Mr. Wallace, there's something really cool I'm going to show you at the end of the hour.
No.
It's on my phone. It's a picture.
Remind me later. The power rule is going to be one of your favorite things. No, you were like, oh my God, why did you let us do this last time? It's probably going to be maybe a little anger. It's going to give us a very simple way to find derivatives of most functions. If n is a rational number, then the function given by f of x equals x to the nth is differentiable, and f prime of x equals n times x to the n minus 1. One less power, and then what goes in front of the term? Which was the original power. But again, it's not that this is the way it works and the last time stuff was, just to do it. The reason why this works is because of that limit definition. It had to go in that order. And we're actually going to look at the proof of this in your book. Look at it. And so once you have this written down, turn to page 264. We'll check out the proof. So again, how this works is, whatever your original exponent is, you multiply by that, and then you lower it by 1. So you multiply by the exponent, that goes in front, lower the exponent by 1, that's the derivative. So as an example that you can go and write, let's say f of x equals 7x to the 5th. Nope, we're close. 35x. See, yeah, the 7 was already there, so I multiplied by that. Yeah. Now, we could have done that last time, but then we'd have to expand out something to the 5th degree, which, yeah, there's a binomial theorem for it. That can be very fun. That's all we have to do. He's doing separately. Wow. It's going to get pretty easy. And this is basic polynomials. It will get more complicated. And there are certain functions where you can't use these power rules because they're not just power polynomials. They've got other stuff going on, like radicals, maybe there's negative exponents, just little other stuff to know. But these are the basic ones. That's why the section is called basic differentiation. If you look at on 264, that proof right underneath that, they're doing the limit definition. So they're saying the derivative of x to the n equals limit as delta x approaches 0 of x plus delta x to the n, whatever exponent you add, minus x to whatever you add, all over delta x, just like we did it last time. So if this was x to the third, the n's would be 3's. This is in general, no matter what n is. On the second step, they expand that out, and that's just binomial expansion. Like if you were distributing or multiplying it out, you get that. Since you have an x to the nth in the front, and then the minus x to the n in the back, what's always going to happen? And we saw that with our problems. The non-delta x terms always canceled out. Then if you look at the delta x's, how many does the second term have? So when you divide, what happens to it? Now, every term after that, how many does it have? Like look at the third term, how many delta x's? After that, it's going to have 3, and then after that, 4. So it's always going to have more than 2. So when you divide, what are you still going to have at least 1 of? And we're doing this as delta x approaches. So what's going to happen to every term after the second? So you're left with the power. That's it. That's the proof. Not overly complicated, but just using what we already knew.
I have a question about that. What's up with delta x?
They're given this for anything, so there may be a whole bunch of terms in there. Like if it was x to the 7th, then you'd have a whole list. You know what I'm saying?
Yeah.
So, but it doesn't matter how many you have because all of them after the second still have a delta x, so they all go away.
Yeah.
And that's why this is the rule. And that's the proof behind it.
So wait, what? Like the one you just showed us, 7x to the 5th. What if it was like 7x to the 7th? It'd just be like 35 or 49x to the 6th.
Exactly. That's it.
So,
That is your first derivative right there. That's the rule. That's all you have to do.
and you just keep doing that.
If you wanted to find second derivative, which you already know about, yeah, but we'll do later, just do it again. Some more examples of this. Let's say part A. Let's say g of x equals 7x to the negative 5th. Now, even though that's a negative exponent, it really doesn't change anything. We just got to think a little bit. Negative 35, x to the negative 6. That's where you got to be careful. With the numbers, you subtract negative 5 minus 1 is negative 6. So that's your derivative. What if I give you f of x equals cube root of x? Can I use the power? How can I rewrite it first? To use power rule, it has to be written as a power. So if it's not, make it so it is. Radicals, you always can rewrite as powers. Whatever root you're taking is your denominator, whatever exponent that has is your numerator. Now take the derivative. So f prime of x is going to equal 1/3 x to the negative 2/3. Now remember, the derivative, what can that tell us about that curve? Yeah, direction or slope, kind of the same idea. So if I want to know, what's the slope when that equals 1, I just have to plug in 1 to what I just got. I get it. It is really quick if it's like this. One last one. Let's say I've got m of x equals 1/x to the 5th. Can I use the power rule?
Yeah.
Yeah, I probably would put it up there. But how do I have to rewrite it? That's a better question. X to the negative. Or if you've got exponents and they're in the denominator, you can write them to negatives. So now our derivative, m prime of x, would equal what?
Negative 5x.
Good.
It's going to be
Don't say that.
Next section, yes, we have multiplication and division rules, but you'll probably like them because it's just rules to memorize. And then you're not going to be able to do it, so you have to. There is no rules.
Whatever you need your life trying to memorize.
All right, so now we're going to take this new rule, do something we did last section, but we're going to do the shortcut. Now with this, that's why I was really strongly recommending you got your 4-1 homework done before today, because you need to do your 4-1 homework using the limit method. You can't use this to do that, because I want you to do the limit. On the test, if I tell you, use the limit definition of a derivative to find this, and you don't do that, you're not going to get any points. You are responsible for knowing that original method when you're asked to do it. But if you're not, then obviously. So we're finding the equation of the tangent line of f of x equals 7x to the 5th when x equals 3. To get tangent line, I need to find the derivative. So look at f prime of x. I don't know why I even did this one. What's it going to be? 35x to the 4th. Is that the exact same one we did earlier?
Yeah.
It's really funny. Since I made up that earlier example randomly. So I'll do the one I already used. I must like 75. Now that I have the derivative, how do I find the slope? Plug in the 3. So we're going to get a huge number, which is fine. So I'm doing f prime of 3, 35 times 3 to the 4th. So what? 2,835. Okay. Now that might seem weird, but to me, that seems fine. Because think about x to the 4th or 5th. That's going to get really, really steep as those values get really high. So even though you're only at 3, it's almost a vertical line. Like it's getting pretty steep like that. So it makes sense that the slopes are a really high number. As we talked about, the slope of a vertical line approaches what? Infinity. So the steeper you are, the bigger that's going to be. And that's going to happen really quick when you have higher degree things. Is that our answer?
Yeah.
Because what's it actually want?
The equations.
Equation. To write an equation, I need the slope, and what other two things do I use? So which one do I need to find still? So I have when x is 3, plug it in to figure out what y is going to be at that point. And I want to know the point, so I'm plugging it into the original one. So I'm doing 7 times 3 to the 5th this time. 1,704. 701. So that's my y. Now I plug them in slope intercept form, easy stuff. 1701 equals 2835 times 3 plus b. Solve for b. Do we know what you get? So multiply and subtract. So negative 6,804. That is what you got. Okay. So then plug it all in. So y equals our slope 2,835, x minus our y-intercept 6,8. The huge numbers, don't freak out if you get big numbers, because we're dealing with a higher degree.
Shouldn't it be plus b to the negative? Oh, no. Oh, it's plus b. Oh,
There you go.
That was dumb.
You caught it. So there you go.
Those two good questions.
Correct. That's not entirely true.
Yes.
That was not. If it's directly related to the subject matter, it's not. That's the clarification.
So what's the point of the 1701?
I had to get it to figure out what b was. I use that over here because I need to know an x and a y to find that one other unknown. So now I know at that point x is 3, y is 1701, and the slope there is the 2,835. Your book is going to give you these as theorems, but they're so easy. I didn't even mess with it. I'm just going to show you an example. And it is based off the fact that with limits, if you had the limit as, x was approaching 0, of a whole bunch of stuff added together, remember you looked at them separately and plugged it in? Because derivatives are limits, you look at them separately, that's your answer. Okay? So it doesn't matter that those are being added. I look at them one at a time, still use the rule, and then just put them all together to get my answer. So if I'm doing, and I want to find f prime of x, what am I going to get for this term? For this term? And for the last term? 0. It's a constant. Derivative of any constant is 0. So there's nothing at the end. That's it.
That's it.
I promise you, you would love power rule. It's one of the easiest things to do. We'll learn how to apply it here a little bit, but yeah. And that's why, again, my title was Basic Differentiation. That's basic differentiation.
You're lying on me, aka really fun section.
Yeah, I'm
not enjoying it.
All right, so application time. And this is where I think this stuff gets really, really cool, because you can actually see, oh, this math actually exists and actually works, even if we did not know about it at all. It explains lots of naturally occurring phenomenon, such as, in this case, gravity. Those of you that had physics are in there right now. Some of this might be a little bit familiar. I know talking to Austin yesterday, your numbers that you used were rounded a little bit more than what we're going to use. But what I have up here is what I want you to use in this course. Yeah, I think you guys use -10. We're going to use -9.8 for our gravity constant. Not a huge difference, but it's what I want.
It's like 5th grade level.
It's probably one of those, I mean, it's one of those like conceptual physics, so it's, hey, we're going to try to teach you physics and take the math out of it, which is like, hey, I'm going to teach you calculus, but we're not going to use any math. It's pretty much the same idea. Oops. Since velocity is the rate of change for the position of an object, the derivative of the position function is the velocity function. And that's a really powerful idea. If I know the position function, I can figure out the velocity at any point in time for that object motion. And this brings us to one of those big ideas we talked about at the beginning of the course. That was one of the problems that algebra fell short with. We could not find instantaneous velocity. We could find average velocity, but we could not find instantaneous velocity. Now we can. This will be easy. I guess that's one of the cooler things about this stuff. As complicated as this stuff is, as far as concept-wise, the math is really simple. The position function that you all need to have memorized is up there.
Oh, no.
And that is the position function anywhere. A half the gravity constant, which just varies depending on where you are, times the time squared plus, if you have a variable with a 0, what does that mean? Original. Usually it's said like v sub naught or v sub 0. It's the initial velocity. So how fast was it moving to begin with? Times time plus s sub naught, which will be your original position. How high up was it? So on Earth, the value of g is about negative 32 feet per second. So you need to know that number. Or if we're in meters, negative 9.8 meters per second. Same number, just different units. And it's not quite exactly that, but that's what I want you to use. Okay. So if you're in Earth, that goes in for g. Okay. Now we'll actually do some problems and look at some other stuff, like if we're on the moon, like how does it change? So we just got to figure out the gravity constant for the moon, do the same stuff. If we were on Mars, this function still works, which is again one of those ideas that I think is amazing. It doesn't matter what planet we're on, that equation answers these kind of things for us. We just got to know what the gravity is, because that's how physics and how our universe works.
Why the crap don't they teach us this in physics?
Because it's conceptual physics, and you've got way too many people in there that wouldn't understand it at all.
So we're gonna look that one up.
We will. First, do a very real world example.
It's supposed to be the ultimate thrill for visitors to Victoria Falls. But this jump is about to go horribly wrong.
Ragdoll.
As the cord snaps, Erin Langworth plunges the remainder of the 111-meter fall headfirst into the crocodile-infested Zambezi River.
It went black straight away, and I felt like I'd been slapped all over. She's in the water!
With her legs still tied by the bungee cord, the Australian student was being dragged downstream towards the rapids, the trailing rope snagging on rocks and pulling her underwater.
I actually had to swim down and yank the bungee cord out of what it was caught into.
Oh my God, who's gonna do something?
Despite struggling to keep her head above the water, she managed to swim towards the rocks to wait for rescuers.
When I was first pulled out of the water, they put me on my back, and so all the water that I'd inhaled meant that I couldn't breathe, so I made them roll me onto my side, and that's when I started coughing out water and blood.
These were her injuries, cuts and bruises. She was treated in Zimbabwe, then taken to South Africa, where doctors were amazed she hadn't been more...
All right. So that brings us to our next example.
Brave soul.
Yeah, we got a brave soul here who decides to go bungee jumping. And I used the data from the video. If they jump from a bridge that is 111 meters above the water and stop immediately before touching, or in our case, didn't stop. Doesn't really matter either way, though. Oops. That if, not at the beginning. I switched that. I forgot to fix it. If their initial velocity is 4.9 meters per second, so that would be she jumps up off the bridge. We're saying her leap was initially 4.9 meters per second, and that I just kind of took a guess at to make the math work out a little easier. But that's what we're going with. You would have to know that as well. We're going to find out what is their final velocity. So we're actually going to be able to calculate how fast she goes. Just laughing in the water.
This is horrible.
What? Yeah, but at that moment when she hit, we'll figure out how fast she was going. And yeah, it'll make it seem even more painful once we figure it out. She was doing pretty good.
Your face is the light.
Not to mention.
Again,
others,
I
like,
love when it's like, I don't know. And to me, it's just really cool that we can take this calculus equation and put it to this. Yeah, and that's why I like math so much. All right, first thing to notice, which units are we getting?
Meters per second.
So we need to use that one. So what's our gravity constant going to be?
Negative 9.8.
Okay. So that's what we need to use. And you get that just by looking at it. So G, negative 9.8 meters per second. Now, if you're really, really, really against using meters, you could convert to feet, but it's not good. So our position function is going to be S of t equals, what's it say to do first? A half. What's half of 9.8? So negative 4.9 t squared plus, what's the initial velocity?
4.9.
4.9. And it is positive because we're saying like, okay, that's her jumping up in the air, and then she makes her descent going down. So she jumps up a little bit, then starts going down. That's why that's positive. T plus, what's the initial position? 111, because that's how high up she is.
So that's how we got the 4.5 of the problems up here.
Yeah.
That was
What was the SO stand for?
SO is initial position. So that's how high up she went from. It's supposed to be like 50 degrees. All right, so to find velocity, what do I need to do with the position function? How do I change it to velocity, but how do I do that? Take the derivative. So we're going to find S prime of t, which is v of t. The derivative of the position is the velocity. Now, an even cooler thing that we're going to figure out later on, any guess about what the derivative of velocity will give us? What's rate of change for velocity? Speed is just absolute value velocity. But acceleration, they're all related. If I take the derivative of velocity, we'll get acceleration. And we'll do that when we start doing second derivatives next time. All right, derivative, what's that going to give a? Easy stuff.
Negative 9.8.
T.
Plus 4.9.
And what's a 111 become?
0.
0. All right. What else am I going to have to figure out before I can actually find the velocity? So I need to figure out t. How do I do that?
Good question.
Time it takes to fall.
Time it takes to fall. So what's her position going to be when she hits the water? 0. So I'm going to take my position function, say 0 equals negative 4.9 t squared plus 4.9 t plus 111. And we need to solve that. Now we'll get 2 answers. We only care about the positive one because she's not going the other way.
We didn't squat there.
Quad 3 will be easy to use, quadratic formula. I mean, it's going to be a decimal, so factoring is not going to be something you want to try to do at all. So you just use quad 3. I just want the positive solution. I don't care about the negative.
And negative 4.9 plus or minus. Plus.
Convert it over to, have quad 3 converted to a decimal for you. Yeah, do that.
5.285714.
So we'll go about 5 point, what was 2.8, what was after that?
285.
Okay, so we'll do 5.29. Okay. So we're going to say our time is approximately 5.29. So really fun 5 seconds. Now that we know what time she hits, I just want to find the velocity at that time. So I'm doing v of 5.29, which is equal to negative 9.8 times 5.29 plus 4.9. And that's going to be my answer. Yeah, so we'll go. Velocity was, say it again, 0.9.
42.
What's the unit? Meters per second. That's why, I mean, that's why everyone was really surprised that she lived, because 111 meters might not seem like a whole lot, but you guys familiar with the idea of terminal velocity?
No.
Terminal velocity basically is like there's a maximum speed you can get up to. So like if you're free falling, like let's say you jump out of a plane and don't use the parachute or whatever reason, there's going to be a limit to how fast you go, and there's a certain amount of time it takes to get there. She didn't quite get to that, but she was getting pretty close because it doesn't take a whole lot of time to get to that. So she was almost going as fast as she could go, and that's why from that height, I mean, as you go down, you fall faster and faster and faster until you get that constant. So that's why everyone's really surprised, because the faster you're going, what's going to happen to the force of impact? Hard. Yeah, it's going to be way hard. So it was crazy that she lived, because she was going that fast when she hit the water. It wasn't very deep. Yeah, head first, feet were tied. So it was pretty amazing that she had some bruises and got some outside. What? Oh yeah, like I mean, just lucky that she didn't drown. And so there you go. And there is how calculus answers some cool things. So gravity constant tells you how fast you accelerate per second. So that's just going to keep going. Like every second it keeps going up that way until it. Okay, I'm trying to think of a good way to play this. Think about like just how gravity works. The closer you are to the Earth, it has more pull on you. So when you start out here, it pulls on itself. But the closer you get, it's actually pulling you in more. So there's more force. So that's why you continually speed up as you fall. That's kind of what's going on there. So it's not that gravity gives you a number per se. I'm having trouble. Right, so that's that.
Gives you a number of X. Why?
Yeah, but you saw me.
Yeah, but it's tournament week.
Yeah.
Stuff.
There is no reason why that shouldn't get done
My
next
back
week.
hurts.
You're probably not even gonna go to the game.
I know.
Yeah,
I got
Another one again.
yeah, tonight.
Miss Lotus, I got soccer every
And
year.
tomorrow.
I believe that.
So,
We don't see Haley at any kind of events ever.
I didn't get to go last night.
I mean, I can do this while
The year before last night. So I'm taking my time coming back.
And this sort of almost,
Yes.
here's a little geeky kind of.
Give me uno momento.
Poor Corn.
I gotta save this before I delete it.